Good morning. Today we are going to discuss about thermoelectric effect. So thermoelectric effect describes the direct conversion of temperature difference to electric voltage and vice versa. So a thermoelectric device creates a voltage when there is a temperature difference on each side. Or we can say that when a voltage is applied to a junction, heat is transferred from one side to the other, creating a temperature difference. This effect can be seen in the vice versa, in the opposite direction also. That means an applied temperature difference causes electric current. So thermoelectric effect describes the conversion of temperature difference to electric voltage and electric voltage to temperature difference. So basically thermoelectric effect comprises of three different effects. They are Seebeck effect, Peltier effect and Thomson effect. So thermoelectric effect deals with the conversion of temperature difference to electric voltage, and it comprises of three different effects: Seebeck effect, Peltier effect and Thomson effect. The Seebeck effect was discovered by Thomas John Seebeck. So Seebeck effect states that when two different conductors, so it should be a couple of elements, couple of metals, and if two different conductors are joined to form a circuit and the junctions are held at different temperature, then a potential difference or an EMF is developed, which results in the flow of electric currents. So see this figure. So this is a thermocouple. Thermocouple means two elements, a couple of thermal elements. These are iron and copper, and they form two junctions, A and B, two junctions. One is kept at temperature T1 and other is kept at temperature T2. Here the temperature T1 is greater than temperature T2. So if these two junctions are kept at different temperatures, then there will be an EMF and current flows through the circuit. The direction of the current is also shown. That current flows from the higher temperature region of higher temperature, junction of higher temperature to junction of colder temperature. So let's revisit the definition once again. The Seebeck effect states that when two different conductors are joined to form a circuit and the two junctions are held at different temperature, then an EMF is developed and electric current flows through the circuit. The magnitude of thermoelectric EMF depends upon the nature of the two metals and on the temperature difference between the metals. So it depends on only two parameters. What are they? Which all metals are used and what is the temperature difference between the metals. So actually this Seebeck was he received medical degree in 1802. So from the University of Göttingen, he got a degree in medicine, but he preferred to work in physics. And Seebeck did a lot of experiments by trying different metals, varying from bismuth to tellurium. So he made a list like this: bismuth, nickel, cobalt, platinum, copper, so on. So this list tells us if the metals from the extreme ends of the list series is used, they will produce more EMF, more thermo EMF. So if the metals are further apart in this series, they will get more EMF than the metals which are close to each other in this series. So this series is called a thermoelectric series. And also the Seebeck effect is reversible. That means if the hot junction and cold junctions are reversed, the direction of the current will also get reversed. So when any of these metals in the series is used to form a thermocouple, the thermo EMF is greater when two metals used are further apart in this series. So it will be giving you high EMF if you use bismuth and tellurium, then nickel and antimony, so on. So the thermo EMF of this couple means the iron and cobalt, is only 1.3 millivolt for a temperature difference of 100 degrees Celsius between hot and cold junction. If we make a thermocouple with, so by the by, thermocouple means it is a junction or of two metals is called a circuit containing two metals having two junctions is called a thermocouple. So a thermocouple made of iron and copper and kept at 100-degree temperature difference, then they will produce a thermo EMF of only 1.3 millivolt. So I have given a list shows the thermo EMF with respect to platinum when the cold junction is at 0 degrees Celsius and hot junction is at 100 degrees Celsius. See if we can not see that the iron, which is the farthermost element in the given list, which is more far than all the cadmium, zinc, silver, and lead, we can see that iron is having higher thermo EMF than lead, which is near to the platinum in this thermoelectric series. Okay, you got the point. So we have discussed about Seebeck effect. So when two different conductors are joined to form a circuit and two junctions are held at different temperature, then an EMF is developed. So this time we are giving a temperature difference and a voltage is produced or an EMF is produced. Now we will discuss about Peltier effect. So actually Peltier effect is the opposite of Seebeck effect. So in 1834, Jean Peltier, who was a French watchmaker, discovered the second thermoelectric effect. So what does this effect states? So this effect describes a phenomenon that a potential difference applied across a thermocouple causes a temperature difference between the junctions of the two of the different materials in a thermocouple. So we have a thermocouple and this time we apply a potential difference. What will happen? There will be a temperature difference between the junctions. So see the difference in Seebeck effect. We applied the temperature difference and we developed an EMF between the junctions. But this time we are applying a potential difference across a circuit and we can see a temperature difference developed between the junctions. So if a current flows through a circuit containing junction of two dissimilar effects, it leads to an absorption or liberation of heat at the junctions. So heat can either be absorbed or given out depending upon the pair of metals. Okay. So Peltier effect is the opposite of Seebeck effect. Here we apply the potential difference and we get a temperature difference between the two junctions. Now we will describe about the third effect that's called the Thomson effect. So Thomson effect was actually predicted and observed by William Thomson, who was later honored by giving the title of Lord Kelvin. So we know that Kelvin scale of temperature and all. So these are both same persons, William Thomson, who was later known as Lord Kelvin. And he discovered this effect in 1851. So what is Thomson effect? Thomson effect states that the evolution or absorption of heat when electric current passes through a circuit composed of single material that has a temperature difference along its length. So in Peltier effect and Seebeck effect, we have two metals. And these two metals have two junctions also. And we are in Seebeck effect, we are keeping the two junctions at different temperatures. But here it is about a single material, a single conductor. And if different portions of the conductor are kept at different temperature, what we can say then electric current is passed through the material. So we have a material or a conductor. It has a temperature difference along its length and we pass an electric current through it. Then what will happen? Either heat will be given out or heat will be absorbed. I will say it once again. We have a current carrying conductor and we have temperature gradients. We have different temperatures at different regions. One region is cold, other region is hot and all. And we pass the current through it. What will happen? The heat will be liberated, heat will be evolved or heat will be absorbed. So this effect was described by William Thomson. So there are two types of Thomson effect. One is called the positive Thomson effect. The other is the negative Thomson effect. In positive effect, it is found that the hot end is at hot potential and the cold end is at 10 degrees Celsius. So heat is evolved when current is passed from hotter end to the colder end. So heat is evolved when we move from hotter end to colder end, and heat is absorbed when current is passed from colder to hotter end. See in the figure, we can see that the portion C is the hotter region. So when we pass from colder to hotter region, that means from A to C in figure A, we can see that we are moving from colder to hotter region, then the heat is absorbed. When we move from C to B, that means from a hotter region to colder region, we can see that when current is passed from C to B, heat is evolved. So metals which show positive Thomson effect are copper, silver, cadmium, zinc, etc. While in negative Thomson effect, we can see that when current is passed from colder to hotter region, the heat is evolved, and when current is passed from hotter to colder region, that is from C to B, the heat is absorbed. Iron, cobalt, bismuth, platinum, etc. are the example, etc. display the negative Thomson effect. So we have explained what is thermoelectric effect and the three different phenomenon which comes under the thermoelectric effect. Now we are going to discuss about how this thermoelectric effect happens. So explanation of thermoelectric effects based on electric theory. We have only a qualitative we need only a qualitative scheme. We don't need any equations and all. So just an understanding is needed about this topic. So we know that all materials are made of atoms, and atoms consist of a positive nucleus surrounded by electrons. You learned about the free electron theory. So the outermost electrons in the outermost shell are loosely bound to the nucleus, and in solids they are almost free. So such electrons are called free electrons, and the ions from which and the nucleons from which the electrons are set apart are called ions. So what will happen? In general, the distribution of the electrons are free. There will be equal number of free electrons and ions in a particular portion of the solid, and overall that portion will be neutral. But when we apply temperature or when we give energy to one part of the material, what will happen? The electrons at that part will gain more energy and they will have higher average speed than those at the coolant. So free electrons at the hot end where we apply the heat. In this figure, we can see that on the left part we are applying the heat and we are giving colder, that means we are cooling the right end. So electrons at the hotter end will have average energy than the electrons at the colder end. So what will happen? More electrons will move from hotter region to colder region. So the hot end of the wire become positively charged than the cold end, because electrons started moving from the hot end to the cold end, and the cold end will have more electrons and hot end will have more ions. That means it will be positively charged. That's not the end. Something else can also happen. If we heat a portion, the electrons will gain energy and they will start to move at higher speed. But not only the electrons can gain energy, but ions, the positive ions will also gain energy. So ions cannot move like free electrons, but they will start to vibrate very violently, so that it will scatter the free electrons in all direction, and it cannot move from the hotter region to colder region. So this will have a negative effect. That means the electrons in the colder region will start moving from the colder region to the hotter region, Even though the electrons in the hotter regions have ion energy, but they are scattered by this ion, they cannot move to the colder region. So electrons will start moving from the colder region to the hotter region, and the hotter region become negatively charged, or the colder region become positively charged. So these two factors compete with each other in every material, and whichever wins this determine the sign of the Seebeck coefficient. So some materials, the hot end become positive, while in other the hot end becomes negative. So this is a brief explanation about the thermoelectric effect. Now we will discuss briefly the laws of thermo EMF. As I have mentioned, the thermo EMF depends on the temperature of the junctions. So it is not dependent on, or it is independent on the temperature of the wires which connect the junctions. So we are not at all bothered about the connections. We are bothered only about the junctions. So we have two metals and they may be connected by different wires which are kept at different temperatures. But we are not bothered about that. We are interested only in the junctions, temperature of the junctions. So the second law says that the EMF is not changed when a new conductor is introduced into one of the metals, provided that both of the new junctions are at the same temperature. So we have an A and B. So in B, we are introducing a new conductor. So in B, now we have two more junctions. If those two junctions are at the same temperature, then this introduction of new conductor will not affect the thermo EMF. And the third effect is like superposition. The law of intermediate metal states that the EMF of materials AC, so we have two material A and C, EMF of materials AC can be predicted if EMFs of material AB and BC are not. Say for example, if V2 is the voltage, Seebeck voltage, if two junctions are temperature T1 and T2, and V1 be the voltage when the temperatures are at T2 and T3, then temperatures T1 and T3 will produce a voltage V3 is equal to V1 plus V2. It's like a algebraic addition. So these are the three laws of thermo EMF. Now we will discuss about the effects of variation of thermo EMF with temperature. So how does a thermo EMF vary with temperature? To study the effect of difference of temperature, we consider a thermocouple of two dissimilar metals A and B. One junction is kept at 0 degrees Celsius and the other junction is kept on temperature of the other junction is increased gradually. It is found that the thermo EMF varies with the temperature of the odd junction. So notice the graph. We can see that the thermo EMF increases till a point, and after that the thermo EMF started decreasing. If the temperature is increased from the cold junction to a temperature called the neutral temperature, the thermo EMF will increase, and beyond the neutral temperature the thermo EMF will start to decrease, and it reaches zero at a temperature called Ti, or temperature of inversion. Okay, beyond temperature of inversion, if the temperature of hot junction is still increased, the thermo in the opposite direction. We can see that Tn minus Tc, the difference between the cold junction and neutral temperature is equal to the difference between neutral temperature and the temperature of inversion, or neutral temperature is Ti plus Tc by 2. It's a mean of the temperature of inversion and temperature of cold junction. So thermo EMF is a property of each material and can be easily measured for a junction of two dissimilar metals at different temperatures. Okay. So these are the discussions about the variation of thermo EMF with temperature. The thermo EMF of a thermocouple is given by the equation E is equal to alpha T plus beta T square. It's a quadratic equation, alpha T plus beta T square, where T is the temperature difference between the two junctions and alpha and beta are the parameters of the material used. When we take the derivative of thermo EMF with respect to the temperature difference, that is dE by dt, That is called the thermoelectric power. Thermo power, or the Seebeck coefficient S. Seebeck coefficient S is equal to dE by dt. Okay. So the thermo EFMF is given by the equation alpha t plus beta t square. As we have mentioned, it depends on the temperature difference, that's a T is there, and on the two metals, and alpha and beta comes from the parameters of these metals or the material used. Now we will discuss about thermoelectric diagram. So a thermocouple is formed of A and B, and we have the equation E is equal to alpha t plus beta t square, and we have thermoelectric power of the C, or the Seebeck coefficient, as dE by dt is equal to alpha plus beta t. If we plot a diagram between thermoelectric power dE by dt and T, a graph between thermoelectric power and difference of temperature is a straight line, and this graph is called the thermoelectric power line or the thermoelectric diagram. So this graph shows the thermoelectric diagram of different metals with respect to lead, Tb, lead, because the Thomson coefficient of lead is 0. So we have taken lead as a reference, and one metal is lead, and the other metals are depicted in this graph. See cadmium, zinc, cobalt. See that we can see that the copper is on one side of lead, while iron is on the other side. So I will show you the series. The lead is in the middle, and copper is on the left side, while iron is on the right side. Got it? With respect to lead, iron and copper are on two sides, and we can see that the thermoelectric line or the thermoelectric diagram of copper lead has a positive slope, while iron lead has a negative slope. Okay. And now we will discuss what is a thermocouple. A thermocouple is nothing but a thermal junction that functions based on the phenomenon of thermoelectric effect. A thermocouple is defined as a thermal junction that functions based on the phenomenon of electric effect. So it is used as an electrical device or a sensor to measure temperature. So I'll illustrate an example. Suppose we have a furnace which have a high temperature, and we need to find the temperature inside the furnace. So we have a thermocouple whose one junction is in the furnace, and the other junction is kept at a reference temperature, say maybe 0 degrees Celsius or 100 degrees Celsius. We have kept it as a reference temperature. And now we can measure the thermo EMF in this circuit, and we can find the temperature of this junction if we know the thermo EMF and the temperature of the other junction. We know the parameters. So E is equal to alpha t plus beta t square, and T is the temperature difference. If we know one temperature of one junction, then we can find the temperature of the other junction. So thermocouple is used, can measure a wide range of temperature. It is a simple, robust, and cost-effective temperature sensor used in various industrial applications, home, office, and commercial applications. So thank you. This is about thermoelectric effect.